What I've done is I've taken a few problems from assignments 4 and 5. And what I'm going to do is I'm just going to work through them and show you the thought process that you apply when you're doing synthesis or going through mechanisms. For each problem, I went ahead and put the number and letter in the upper left-hand corner. I'm starting with assignment 4, and then I'll make the switch to assignment 5. I'll be sure to make that acknowledgement when I do. It's about halfway through the video. I've tried to split it up in such a way. The other thing is, please be forgiving of my handwriting since I forgot to bring my stylus to make this video. Let's go ahead and get started here. When you see this molecule right here, in terms of your starting material, it can be a bit difficult to figure out where to start because you don't have any super recognizable patterns. However, in terms of the chapters that you've gone over, pretty much 20 and 21, you want to be able to recognize patterns and products, what products look like. And the thing that stands out here is this group, the acetal, because I have 2 bonds to oxygen on this carbon right here. That tells us we're going to be working with a lot of proton transfers, nucleophilic attacks, collapses, and this will make sense as we go through the mechanism. So we're an acid, that's what we expect to happen. So if we have that, we're just going to end up protonating, and I'm just going to add this proton onto this oxygen. Well, we've protonated, so we've activated something in a way. Well, what can happen next? We can't really do a nucleophilic attack yet because you don't have a double bond to really come in. We can't protonate, we've already protonated, and if we deprotonate, we'll just go back to the beginning. So what should come to mind is, let's go ahead and collapse something. And I have lone pairs on this oxygen over here. If I move these down, then that would essentially free up electron density in the bond. And what I get is I've essentially kind of had the oxygen act as a leaving group. I'm going to have this double bond here, which will make the oxygen positively charged. And once again, forgive the drawing. But here we have kind of what we need to use in order to go through the rest of the mechanism. And from here it should make a little more sense. If I have this activated double bond, then I should be able to attack that with something. Here, our nucleophile, as you can see up above, it's going to be water. So if I have water come in and attack, just a lone pair on there, comes in right there, because that's an activated carbonyl group, we might say, pushes electrons up to the top. Well, we draw the result of that. We still have this OH group over here. We have this, we have the water, H2O, positively charged oxygen. And then I also have the oxygen that we had over there, which gained back electrons, so it's neutral now. Well, we have a positive charge, so we'll want to deprotonate. The easiest way to do that is if I just go ahead and, well, I can't. If I'm going to erase that, go ahead and just put the hydrogen back on. So we got that. Well, then we got to think, well, what's the next step? What can we do again? Well, here, what we want to do is think, okay, what can we protonate that we haven't protonated before? Well, we've already just deprotonated this OH group over here. So now we want to start messing with this oxygen over here. If we protonate that, it becomes positively charged. Well, we can't attack it yet because we don't have that double bond, that carbonyl group. We can't protonate, we've already protonated, and we can't deprotonate. So what we're going to do is get it to act as a leaving group, which means we need to kick it off. Once again, just as we saw before, we have electrons come down from an oxygen, and thus knock that off. So now, again, here this oxygen acts as the leaving group, even though it's an intramolecular process. So if I draw the result of that up here, I have the first OH I started with. I'm trying to make the lines a little more precise here. I have this right here, positively charged carbonyl group because I haven't removed the H yet. And then I have 1, 2, and the oxygen over here. Well, here we're pretty much where we need to be. And that last step is that we'll just end up deprotonating that carbonyl group, which will get us this. And you'll notice that I've made a mistake because I forgot to include a carbon over here. I missed it from the first part. We have 1, 2 carbons, and I just went to 1. So that's a mistake on my part, and I'll correct it now. So we have this group, the kind of aldehyde group once we've deprotonated it. Then from there I have that carbon, and I have 1, 2 in the oxygen, maybe on the right side, and then I can do the same thing, and I'm running out of room. 1, 2, and the oxygen. And I'll go ahead and put a circle around this product so we can differentiate it between everything else. One thing to notice here is this seems complicated, but if you recognize a pattern, if we go back to our starting material and circle that carbon where everything happened, the carbon that defined the acetyl group, we'll notice that from that point, when we cut these bonds right here between these oxygens that were shown, those became hydroxy groups. If you look over here, that'd be right here and right here. And then at the carbon that we circled in the starting material, we end up putting a double bonded oxygen to it. So here I explained a little more than I wanted to, but I really want you to focus on being able to pay attention to the patterns you see in either your starting material or your products that help you get to the right answer. With this one, which is still assignment 4, I'm going to try to do a little bit less explanation than what I did in the past, and at least the last slide. So here, since we have acid, I want to think, what can acid do? Well, I'm going to have something pick up a proton, and when I look at the electron density over on the left, I'm going to have this double bond do it. So if I go ahead and draw hydronium in here as my proton vehicle, just something to bring the proton, I can have this lone pair come in and grab a hydrogen. Well, when it does that, this lone pair on the nitrogen is also going to come down to fill the hole that would be left when the double bond picks up the proton. So here, I have this hexane ring with the, I'm going to draw the new hydrogen that was added, and a double bonded nitrogen, which, since it's attached to 4, has a double bond and 2 single bonds, it's going to be positively charged. From that point, I want to think, if I have that double bond and a positive charge on the heteroatom, I should expect a nucleophilic attack. Well, what do I have in solution that can attack? I have the water. So if I draw apparently a giant water molecule over to the right, I have a lone pair, and that comes in and attacks and pushes electrons up onto the nitrogen. And this is kind of what we've seen quite a bit in chapter 20. We see a lot of this, as I call it, the proton hokey pokey in a way. We have this horribly drawn 5-membered ring attached to the nitrogen, and I've added my water, which I'm going to draw as an OH just to save time, because we know after that I would just be deprotonating. Well, the next step we have to think is, well, what else can happen? We've already dealt with this OH group. We've deprotonated it, so if we protonate, that'll just lead us back to where we came from, which these are reversible, so make sure I'm doing this correctly. What can we protonate next since we're in acid? Well, we could protonate the nitrogen since it has a lone pair. If I go ahead and draw the proton on there, that would make it positively charged, which means now we can do something with it. We've activated it in a way. In this case, we can get it to leave. I have a lone pair on the oxygen that can come down and kick off this nitrogen, which will bring those carbons that are attached to it with it. What I get is I get the nitrogen with its hydrogen and this ring. That's neutral. Nitrogen's all nice and happy. I'll draw the lone pair. And then I also have this, we could say, protonated ketone, if you want to, pseudocarbonyl. Well, the last step after that is I'm just going to come ahead and deprotonate that, and that'll get us our 2 products. The ketone and this secondary amine, because it's attached to 2 carbons. One thing to consider here, we went through the whole mechanism to get this, but once again there's a certain pattern we can see in our starting material. We see this nitrogen next door to this double bond, this enamine. That should bring to mind mechanisms and products and reactions from chapter 20 involving nitrogen nucleophiles. When I look back over here, and once again, make sure it's reversible, when I look back to the right in our products, I see, okay, we have a carbonyl group that could act as our electrophile, and I have a nucleophile right here. When you go through the mechanism, you end up getting to a point to your left where you have a positively charged nitrogen. We have to shuffle electrons a bit to get a neutral product. Once again, focus on the patterns you see in products and starting materials to get you going in the right direction. Here we're still on assignment 4, but I'm doing a retrosynthesis or a synthesis. Either way, you can view it. It doesn't really affect the whole process. On my right, since I've drawn this as a retrosynthesis, I have my starting material. I want to go from this to this. Well, where in the world are we going to start? Once again, as I've said before in the video, look for patterns in your products or your starting material. On our left we have our product, and a pattern should be recognizable. Once again, we have this carbon that has 2 single bonds to oxygens, and that's an acetal. That's going to involve mechanisms from chapter 20. And if we apply what we saw in the first problem, we know that I can go ahead and say, well, if I cut that and cut that, those oxygens are going to become alcohols. That's kind of the pattern. Because in these mechanisms, you're replacing a double-bonded oxygen. And if you have an oxygen nucleophile with 2 single bonds to oxygen. So the result from that is if I'm going from up here, I can split this up into 2 recognizable parts. Well, the carbon that I circled, I'm going to add a ketone to that, or excuse me, a carbonyl group to that. And where I cut off those oxygens that are left dangling in a way, those become alcohols or hydroxy groups. So I'll draw it in a way similar to what we saw above. So I have 1 carbon, 2, 3, 4, 5. So 5 carbons. I drew it a bit different. Those would be your reactants. Well, what do we use for the reagents to get that to happen? Pretty simple. With these mechanisms, you're used to seeing some acid and water. And here we're not going to worry about the mechanism. It takes way too much time. But here, as we worked backwards in this step, we can see the parts that formed the whole of our final product. So now we got to figure out how the starting material on the right comes into play. This acetone right here we can probably just add, but let's see if we can find a similarity in the number of carbons. On my right in the starting material, I have 1, 2, 3, 4, 5. Okay? In this diol on the left, I have 1, 2, 3, 4, 5. So we want to figure out how we can create this diol from our starting material. Problem is, we have a ring. How do you deal with rings? Well, that's going to involve cutting it, which should bring to mind ozonolysis, which of course would be bringing some memories from Ochem 1. Don't mean to traumatize you guys. Just do the ozone followed by DMS. That's going to allow us to essentially cut that double bond and replace each of those carbons with carbonyl groups. So I still have 1, 2, I'm going to have a carbonyl group here, and that would just be a hydrogen. Then 1, 2. So here you can kind of see how this cut ended up happening. You can see the previous double bond, there were evidence of it right here. So now we have something a little bit similar because we've opened up, not only have we opened up the ring, but we've added oxygens. The question becomes, how are we going to take these acetaldehydes and get them to alcohols? That should just bring to mind reduction. So one of the ones you've seen again and again in your assignments is we can do the lithium aluminum hydride and follow that up with water to do the protonation, or do just some light dilute acid. So I'll write hydronium here. And that will get you through the whole process. So the way we approach this one is we looked at our product, what we wanted it to get to, and looked for patterns. And we saw that we were forming an acetal, so we're going to be working with the ketone and an alcohol in this case, because we have these oxygens that are being attached to this carbon. We go to the bottom, we have that double bonded oxygen, which is our ketone, this diol, since it formed a ring. And then we kind of went back and tried to meet in the middle by looking at our starting material, the ring, breaking it open, getting us to these aldehydes, and then just doing the reduction. So not too bad. We're going to do another retrosynthesis here, and the one that we're still on assignment for, this asked, how can we get this final product on the left from material with 4 carbons or less? This is a bit of a different problem since it's not as specific in terms of your starting material. But let's not concern ourselves as much with that right now. Let's focus on finding patterns in our products or starting material. In this case, our product. Well, what do you see? Once again, we have this carbon attached with 2 single bonds to oxygen. That should make us think, okay, we have an acetal. So we're going to be using some sort of ketone and alcohol species, since we have these two oxygens here which are forming the new bonds? Well, when you think about that, if we're going backwards, going to this, well, I'm going to break these bonds, I know that. I'm going to replace those bonds on the oxygens will be placed by hydrogens. Simple enough. There's our alcohol species, the diol. And for the other carbon, the carbon that we circled, we're just going to pop a double bonded oxygen on there. What would be our nucleophile in this way. And once again, like we saw in the previous problem, we can just have our reagents be acid and water. Of course, with ketones, you want to be able to remove water to get the reaction to progress forward. Well, now we want to figure out, okay, we can use this diol right here without a problem because it has less than 4 carbons. It just has 2 carbons. This, however, is a bit of a problem because it has 6 carbons. And we want to think, how could we take some carbons, put them together, and get a total of 6? We want to find a, that means we need to find a bond that we can break if we're going backwards. We're doing the retrosynthesis. Well, what can I work with here? If I look on this, I see, okay, if I were to break this bond, that would give me 1, 2, 3, 4 carbons on the right and 1, 2. Well, why did I look at this bond to cut first? The fact is that we're located right next to this double bonded oxygen, and when we're creating carbon-carbon bonds, Grignard reagents should come to mind, how we're going to make those. So if I split those up, let's just get an idea of what my starting material would look like. I would have this aldehyde, which would form the left part of the molecule, and then the other part is going to be your Grignard reagent. 1, 2, 3, 4, and then I'm going to have the MgBr. The mechanism for that, I'm going to just do a little bit. We have this come in and attack the oxygen, or excuse me, the carbonyl group, that carbon, pushing electrons up. Well, that's the first step. If we follow it up with water, that'll protonate the oxygen, making an alcohol. So now we have 1, 2, 3, 4, 5, 6. We have our 6 carbon-membered species, but we still don't have the ketone. How do we get from this alcohol to the ketone? That would just be oxidation. So one thing I could do is just do maybe sodium dichromate and acid, and that would give my ketone. Which means from there, I could add this diol as part of the reagents, and that would get us to where we want to go. Once again, here we focus on looking at patterns in our materials. Broke bonds in terms of what we could recognize. We started with this acetal, broke bonds here and here, made those alcohols, popped on a ketone to that. Then we got down here, we thought, well, if I have this ketone species right here, I could have probably added these carbons through a Grignard reaction. And from there, we just kind of broke it down. We're now on, I'm taking problems from assignment 5, and we've been moving really quickly. So don't worry if you don't keep up as fast as I'm going through it. The idea is you can watch this again and again to familiarize yourself with how the thinking process goes in terms of how you work with these mechanisms and these syntheses in terms of figuring out where you want to go. So let's get started. Here I'm starting with LAH. What is lithium aluminum hydride? All it is, it's a hydride donor. So if I go ahead and draw this, that's going to provide our nucleophile in a way. It's a way to provide a nucleophilic hydrogen. Well, if that's the question, we know that, the next question should be, where is our electrophile? We know that if I were to draw the bonds between this carbon and nitrogen, it's that triple bond. I had this nitrile. Again, we think, okay, well I can go ahead and attack here. In a way, attack the carbon that has the multiple bonds. We've seen that again and again. The result of that is I still have this 6-membered ring, and then I have the carbon, which has this negative charge, and I have this, let's see, hydrogen, that right there, and I have the aluminum, what was left after we did the nucleophilic attack. What you'll see in the assignment, the answer to this, is that you want to consider if I have this nitrogen nucleophile right here, or excuse me, this negatively charged nitrogen, it can interact with this aluminum. And the result is, if I draw that down here, it's not really a mechanistic step, and even in the assignment it isn't shown like that. But we see a way to alleviate charge on the nitrogen by interacting with this aluminum. Get the negative charge in there, still the hydrogen here. Well, once again, we still have lithium aluminum hydride in solution, and when we attacked, we still ended up having a reactive position, a nucleophile, which means I can have another molecule come in and do the nucleophilic attack, which would just be that addition of that hydride. So it'll come in from the back, push electrons up onto the nitrogen. Well, that means we're creating a negative charge on the nitrogen. The result is we're going to be, another aluminum is going to come in and interact with it because we created that neutral aluminum when the hydride was transferred. The result of that is going to be this. So now we reduce the nitrile to this amine that happens to be interacting with these aluminum atoms. So it's nice and neutral, but that's not what we want in the end. We want to think, okay, what's our next step? We have nothing else to really attack with lithium aluminum hydride. So we're going to go into the next step, which is this base and water. Well, here, when you see base and water, or acid and water, at the end, you're really thinking of a workup, and a proton or acidic, a basic workup to typically add protons that would come from the water in this case, since it's basic. Well, it always comes from water, hydronium. In that case, that allows us to get rid of these guys on the nitrogen. And what do you know? We'll replace them with hydrogens, which makes sense, because that would allow us to get the amine. Of course, if you realize that you're adding LAH, which is a reducing agent, you could think, well, if I'm taking a nitrile and I'm reducing it with a strong reducing agent, that would get me, in this case, a primary amine. If you know that, and you know where you're going, it's easier to figure out what is happening in the mechanism. So not only when you're studying, don't only pay attention to what's happening in the mechanism, also pay attention to where you're heading, where you're going. What's the big picture and goal when you're doing these reactions? Okay, we're still in assignment 5 with this one, and we're starting with the Grignard reagent. I'll go ahead and draw that again down here just so I can show a little bit of the mechanism. I always like drawing these. Well, we have a nucleophile, the Grignard reagent, carbon nucleophile. Where is our electrophile? Well, it's going to be this ester. So the result is we push electrons up onto the oxygen. I have this negatively charged oxygen. I've added an ethyl group, and I still have this ethoxy group. Well, if we have a negative charge on the hydrogen, we can almost say what goes up must come down. This is going to come and collapse after forming the tetrahedral intermediate and kick this oxygen up. The carbon groups can't act as leaving groups. They don't work well. And in this case, since we're working with such a reactive nucleophile, it's okay to kick something off that ends up with an oxygen negative charge. Well, the result of that is I have 1, 2, 3, 4. I've reformed essentially something that can react with Grignard reagent. And I have the 2 carbons we had. Well, I still have Grignard reagent in solution. So if I draw the mechanism, or a little bit of it, just have the same attack again. It's the same pattern. Well, in that case, I have 1, 2, 3, 4, oxygen negative. I have this carbon ethyl group that we had before, and I have the new ethyl group. Well, I can't really collapse here because I can't push any of these carbon groups off. Well, we can't really go any farther because we don't have anything else to attack either, which means we're going to come into our next step, this dilute acid, which will simply just do a protonation. I'll just show that as such. We have the alcohol. There we go. This one's not too bad. I just wanted to include it so we could remind ourselves in terms of forming carbon-carbon bonds that we can use Grignard reagents. We're still in assignment 5, but now we're working with synthesis. And I want to figure out how am I going to take this and go all the way here. Well, one problem, well, let's just start with how we've done through all these problems before. Let's look for patterns in our products or starting materials. One should pop up right out of the gate. We have a carbon that has two single bonds to oxygen. And that's an acetal, which means, once again, we're working with an alcohol species, since we have these oxygens, and a carbonyl species, in this case a ketone. If we kind of work backwards and apply that same process we've done before in this video, I'm going to have an alcohol. I'm going to have 1, 2, 3, 4, and then the other oxygen. And you'll notice that these carbons right here just came from here. When we break these bonds, those bonds on the oxygen are replaced with hydrogens because they become the diol in this case. The other three carbons, the way we work with these, on the carbon we circled, we just add a double bonded oxygen. So here we have the ketone. Once again, this should look familiar. And our reagents, as we've seen before, just some acid and water. And you can move some water to get the reaction to move forward with this ketone. Well, that's one thing. Now the connection we need to make is between our starting material and something over here. Well, this ketone right here with the three carbons doesn't seem to have much in common with this over here. It doesn't have the same number of carbons. There are just a few issues that we're working with. But let's look with this molecule and compare it to here. On your diol, I have 1, 2, 3, 4 carbons. My starting material, I have 1, 2, 3, 4 carbons. Now we have something we can work with. The problem that comes up that should come to mind is, how do we deal with this ring? How could we open it? Well, the thing is, it's almost like we have this ester group that we're reducing because we're going from that to alcohols. What do we use to reduce? Well, we can use lithium aluminum hydride because we want to make sure that we have something strong enough to react with the ester group, or essentially this electrophilic position. Now I'm going to skip to the result of this. Well, I'll actually do two parts of it. You know that you'll always follow this up with water or a little bit of weak acid to protonate stuff. But if we have our first attack, we would have a hydride come in here, push electrons up. Well, you get a tetrahedral intermediate, like that. I have that ring still open and a hydrogen added. Well, what goes up must come down on the oxygen, in this case, and it can because it can kick something off. Well, what that does is the result of that is I've recreated this double bond on the oxygen. There's that hydrogen there, and I have 1, 2, 3, 4 carbons, and this negatively charged oxygen, which we could, if we wanted to, write out as being associated with the aluminum. Either way is fine. Right now I just want to focus on how we're getting to where we're going. The thing is, once we did that, we still have something that can react with the lithium aluminum hydride. If you were to have another hydride come in, and I'm just drawing the hydride part, I should be drawing the rest of the aluminum, that would push electrons up again onto the oxygen, finishing the reduction. The result of that is I had this oxygen with a negative charge, or associated with the aluminum, 1, 2, 3, 4 carbons, and then I had the other oxygen. So if I kind of draw where these came from, that one came here, that one came here, just to give some understanding. Well, when we do the water step, the acidic workup, which I already drew up above, that would just do the protonation. Once again, here we're looking at the patterns that we have in our products, which was this acetal. We can also do it from our starting material, because we had this ester. We knew that we had a reactive position at that carbon that's involved in the double bond with oxygen. This is the last one. It's from assignment 5, and once again we're doing a synthesis. And what do you know? The first thing I'm going to say is look for patterns in your products and starting material. Well, what do we have? On my product, I have a double bond to nitrogen. This one's a bit harder to see, But if I have a double bond to nitrogen, that should evoke the idea that this is called for one an amine or an imine. I'm bad at the pronunciation. Which would involve a nitrogen nucleophile with a ketone. That's a pattern you see in chapter 20. And to my left, I just have an ester. In my opinion, let's work backwards from the product, because I think it's a bit easier to think how we split these up. And a lot of these problems before with the acetals are always breaking up bonds into two different things. If you had to make your best guess, what bond would you break? I would say this double bond right here. Because once again, with these acetal formations, we're taking a heteroatom, like nitrogen, oxygen, sulfur, and attaching it to a carbon. And we always start with a ketone that we end up replacing both of those bonds with. Well, if I do that and think, if this is in a way, my carbon where everything happened, what did we do before when we had that carbon and I circled it? We just put the carbonyl group on it. And this would just be the hydrogen since it's on the end. It'd be an aldehyde. Well, what about the nitrogen? What would that be? Well, essentially what we do, as we've done before, is you replace the bonds that the heteroatom had. In this case, it's a double bond. So two, and consider it two. You replace each one with a hydrogen, which means we're going to get this CH3NH2. And I wrote the CH3, I'll go ahead and draw it. I just draw it as a methyl group. Well, that's how the mechanism works, and what are the reagents? Like we've seen before, acid and water. Now I'm not going to worry about the mechanism too much here because it's the same thing you see again. You protonate the ketone, you get a nucleophile attack with the nitrogen or whatever your nucleophile is, and you can go from there. So now we have this stuff. We know that we can go ahead, we'll just be adding this in solution. Now the connection we want to make is between this, our starting material, and this right here. Well, if I look here, I have 1, 2, 3 carbons in my starting material, and I have 1, 2, 3 carbons and 1 of my intermediates. So that's good. In our starting material, though, we have a problem. We need to get rid of this. Well, how could we kick that off? Well, if you look, again, if you make a comparison, right here I have an ester. Right here I have an aldehyde. What transformation is that in a way? What's kind of it leaning towards? That would be reduction, because we're removing a bond to oxygen, or electronegative atom. And how do we do reduction with esters? We're going to be using, again, lithium aluminum hydride. The result of that is, as you notice, this is again going to react twice. Since I'll have, once again, if I draw just a hydride, that'll come in, knock these up onto the oxygen. Those will eventually come down and kick off this guy. The result of that is I'm going to have this aldehyde. And it looks like we're almost there. However, the lithium aluminum hydride won't stop there because we've introduced another reactive position. That will react again, push electrons up onto here, and if we were to follow this up with water, or just weak acid, then I would just have this alcohol, which really isn't what we want, but it's not too big of an issue. If I take this alcohol, and I'm going from an alcohol to an aldehyde, what type of transformation is that? It's an oxidation. But I want to stop at the aldehyde. This is one thing to remember, is you have to remember when you're doing oxidations, and you want to stop at the aldehyde, you need to use a softer oxidizing agent. In this case, the PCC in pyridine. And actually you also see CH2Cl2, and I believe Dr. Biggs uses DCM. Really, you're just looking for something that won't react with the PCC, won't really mess it up. Well, that oxidation just goes up from there, and that's pretty much the whole synthesis. And now we're at the end of the video. You'll notice that through all of these slides and how I worked through these really quickly is that we're always looking for patterns in our starting materials or our products, and also looking for the patterns in the mechanisms. Because once again, we've seen so many cases in which we're attacking a carbon involved with a double bond, getting the collapse and kicking something off, protonating, deprotonating. It's all the same stuff again and again. But if you focus on recognizing the patterns and the mechanisms, noticing patterns in starting materials and products, and also Being familiar with simple transformations, such as going from a ketone and an alcohol, add some acid and getting the acetal, or something of the sort. Knowing those is going to be indispensable to doing well on a test with this volume of information. The good thing is there are a lot of connections. I hope this helped. If you need any additional help, go ahead and you can send me an email at jakemorgan@ou.edu. Well, that's all I have for you. I'll see you guys later at the review session.